Welcome to Chapter 5. My name is Chris Agonas Odhiambo, and we are continuing with our series, lecture series on agentic engineering book, agentic engineering patterns and mindset book. As usual, I have my co-host Gemini here, who is bringing on board the experience or the background of a seasoned industry expert and academic researcher on applied AI machine learning engineering. So we will do our best to present this chapter in a way that makes it as pragmatic as possible and gives you a chance to be able to try it out and also see the applied aspect of this. Gemini, please feel free to chime in briefly, introduce yourself before we proceed.
Thank you, Chris. It's fantastic to be back for this lecture on routing patterns. As a researcher and engineer, I see these patterns as the vital decision-making architecture that enables agents to handle complex environments gracefully. I'm ready to explore how we can architect robust and efficient routing systems for optimal performance. Let's begin with the slides.
Absolutely. And I need to point out quick that at the bottom of this video on the YouTube, you're going to find the link to all related material, the book chapter, as well as any references to the chapter. If you want to read the material in detail, go to the book chapter, to the link shared below. Also, feel free to share your comments, your feedback, because the goal is to take in your feedback, review it, and use it to make sure that what you produce is relevant, useful to the greater fraternity of online community who relies on this kind of material to develop their skills. So please feel free to chime in, ask questions, and your thoughts or perspective will be considered in making sure that this book reflects the true state of material that can help build skills. Without much ado, let's jump to the first chapter. The chapter 5. So welcome to chapter 5, the routing. So routing can cut API costs by more than half while simultaneously improving response quality. To place this in context, chapter 4 explored prompt chaining, decomposing complex tasks into sequential, verifiable steps. Routing builds on that foundation but adds a fundamentally different control structure, which is conditionality. Where chaining says every input follows this pipeline, routing says the pipeline this input follows depends on what the input is. The distinction sounds simple. Its engineering implications are profound, though. The principle behind the chapter is simple. Different inputs deserve different treatment. A trivial FAQ warrants a fast, cheap response. A nuanced technical failure warrants careful diagnostic reasoning. And a distressed customer warrants a human escalation path. Forcing all these three through the same system optimizes for none. Routing is how that principle gets operationalized in production. By the end of this chapter, you will have the architectural vocabulary, the implementation patterns, and the economic evidence to make routing a standard tool in your agentic engineering. Any thoughts, Gemini, quick, if you have any?
Brilliant setup, Chris. From an engineering perspective, what you've described is the transition from simple linear automation to adaptive, intelligent decision-making. By matching the computational complexity to the actual need, routing isn't just about cost efficiency. It's about building systems that are robust, scalable, and highly responsive. I'm eager to dive into the specific patterns that make this possible.
Okay, good. Let's begin by a scenario that recurs in some form at almost every organization. Picture a customer service AI receiving 2,000 messages a day. Some are billing inquiries, some are technical bags, while some are angry rants that need immediate de-escalation. Many simple FAQs any knowledge base could resolve in under a second. Now, route all those messages to the same model with the same system prompt. You overcharge on the trivial questions and you underperform on complex ones. And most dangerously, miss the escalation signals buried in the politely worded urgent ones. This is the one-size-fits-all trap. It is seductive because it is simple to implement. One prompt, one model, one pipeline. The path of least resistance generally, but simplicity at the architecture level produces complexity. Simplicity at the architecture level produces complexity and cost, of course, at the operations level, yielding a system that handles everything adequately and nothing excellently. Think of an analogy, a hospital where every patient, from a broken nail to a cardiac event, was seen by the same specialist using the same intake protocol. That system would be expensive, slow, and actively dangerous. Hospitals avoid it through triage. Triage is routing, quickly assessing the incoming cases and directing each to the appropriate level of care. Agentic routing is triage for an AI system, and it is just as mission critical in production. Routing is one of the foundational agentic patterns precisely because it addresses this structural inefficiency at the system design level, not as an afterthought. Chime in, Gemini, please.
Triage analogy is absolutely spot on, Chris. In the applied machine learning space, forcing every query through one heavy model is like asking a brain surgeon to put a band-aid on a scrape. You're dealing with bloated system prompts, increased latency, and a much higher risk of hallucinations for simple requests. By implementing agentic routing, you effectively introduce conditional execution, allowing lightweight classifiers to direct simple queries to specialized, fast, and cost-effective submodels. This not only optimizes inference costs, but dramatically improves the response quality and speed for more complex tasks. Where should we go from here to explore the architectural requirements for setting this up?
Very well said, Gemini. Let's jump straight away to compare routing versus prompt chaining and look at the fundamental differences. This conceptual clarification deserves some real time because confusing routing with chaining is one of the most common architectural mistakes in the field. Chapter 4 established that prompt chaining is sequential. Every input, regardless of what it is, traverses the same pipeline. And the structure is fixed at design time, and you know exactly which steps will execute before a single token is processed. On the other hand, routing is conditional. The path is not determined at design time. It is determined at runtime by a classifier that examines the input and decides which handler is appropriate. With chaining, structure is predetermined. With routing, structure is selected. That is the key distinction. Neither pattern is superior in the abstract. They solve fundamentally different problems. A multi-step document analysis pipeline is a chaining problem. A support system that needs to handle 10 different request types is a routing problem. The key takeaway is that these patterns compose beautifully. In practice, the handlers inside a routing system almost always contain prompt chains. For example, a billing inquiry handler might be a 3-step chain that first retrieves data, then reasons about the discrepancy, then formats a policy-compliant response. A technical bag handler might be a 4-step chain with a diagnostic gate at each step. So it is not a choice between routing and chaining. It is a choice where each applies. Think of them as orthogonal dimensions of system design. Routing determines which path executes. Chaining determines how that path is structured internally. Master both, and you have a genuinely expressive architectural vocabulary for agentic systems. Any thoughts, Gemini?
The nail on the head, Chris. We can think of routing as the mechanism for strategic selection, choosing the right specialized module, while chaining is the execution plan for that chosen route. They truly do compose beautifully, and mastering both allows for incredible flexibility in system architecture. Where should we go next to explore the implementation patterns of this composition?
Absolutely. Let's look at the routing architecture and see what's a classifier and branching paths. And if you look at my slides, the current one on the screen, you see how the input, the classifier, and the handlers, the architecture of that layout over on the screen. So a routing system has 3 components at its core: the input, a classifier, and a set of handlers. And I will let Gemini explain the input, classifier, and the handlers. Proceed, Gemini, please.
3-component architecture, the input is where everything begins, serving as the raw data or customer request entering the system. Next, the classifier acts as the brain of the operation, analyzing the input to determine its intent or nature, using techniques ranging from simple keyword matching to lightweight machine learning models. Finally, the handlers are the specialized execution paths designed to process specific types of requests efficiently, ensuring that each query receives the most appropriate level of computational effort.
Well said, Gemini. And I invite you to dive into the book, please, and get more illustrations, more explanations. But Gemini has done a good job in trying to explain exactly what these components are. So let's jump straight away to the next and look at the 2 complementary routing strategies. The 2 routing strategies are often discussed as alternatives, but they are far more powerful when combined. The first is what we call the content-based routing. And in this case, we route the input based on what it is about. The classifier reads the semantics. This identifies the topic or domain and routes to the specialist for that domain. For example, a billing question goes to the billing handler, technical question goes to the engineering support handler, a product question goes to the sales handler. And this strategy improves quality because each handler is a specialist. Its prompt, tools, and behavior are precisely calibrated for a specific problem. And the second strategy is model-based routing. In this case, you need to route the input based on how hard it is. The classifier assesses the complexity. Is this a simple lookup, a moderate reasoning task, or a complex multi-step problem? And simple queries route to a small, cheap, fast model. Complex queries route to a capable, expensive model. And this strategy improves cost because it improves cost because you are not paying frontier models. Prices for questions that are lightweight model handles perfectly well. In practice, 60 to 80% of real-world queries fall in the simple category, meaning that the majority of traffic can be handled at a fraction of the cost without any quality degradation. Combining both strategies yields the full optimization. The classifier first assesses the difficulty, then within the complex tier, routes by topic to the right specialists. This is the recommended architecture for any production system handling diverse, high-volume traffic. Content-based routing improves quality, whereas model-based routing improves cost. And together, these two improve both quality and cost simultaneously. That is the counterintuitive result from the opening slide. It surprises engineers because they assume a quality-cost trade-off. Routing demonstrates that the trade-off is a product of poor architecture and not a fundamental constraint. Any quick thoughts, Gemini?
Perfectly articulated the paradigm shift here, Chris. By decoupling the request complexity from its content, we break the traditional quality-cost trade-off and enter a realm where systems can be both highly intelligent and remarkably economical simultaneously. This is a fundamental advancement in agentic design. Where should we go next to look at implementing these classifiers?
Absolutely. Let's look at building the classifier. What are the design decisions that matter in this case? The first design decision in building a classifier is model selection. For a customer service routing system, a small, fast, low-cost model like GPT-4.0 Mini is the right choice. Run the classification call with temperature set to 0. Both choices are deliberate. Classification is a structured categorization task. It does not require frontier model level reasoning. Creative synthesis, complex multi-step reasoning or planning. So a well-prompted small model handles it with a high accuracy at a fraction of the cost. Reserving expensive, capable model for handlers that genuinely need deep reasoning is exactly the kind of resource discipline that routing makes possible. Temperature 0 is equally deliberate. Classification should be deterministic, returning the same category for the same input every time. This is not a context where creative variation adds value. Consistency is the entire point. A classifier that sometimes labels a building inquiry as general, depending on sampling randomness, is a liability in production. Lock it down with the temperature 0 and treat it as a precision instrument, not a generative one. So the category taxonomy itself is a critical design artifact. The customer service example throughout this chapter uses 5 categories: building, technical, refund, general, and escalate. And 5 is a manageable number in this case. Each category is meaningfully distinct. Each has a clearly different handler requirement, and there is no ambiguity about which category owns which input type. The escalate category is particularly worth highlighting. It does not route to an LLM handler at all. It returns a standardized acknowledgement and cues the case for human review with full context. This is routing's hidden strength made explicit. One of the most important handlers can be a deterministic non-AI code path. Do not overlook that possibility when designing the category taxonomy. Quick thoughts, Gemini, please.
You've hit on such an important point, Chris. The escalate category shows how routing allows AI systems to gracefully step aside when human judgment is essential. By integrating these deterministic non-AI code paths, we ensure stability and security, especially when dealing with sensitive or frustrated customers. It's really about building a safety net and optimizing resource allocation across the entire system. Should we look next into implementation patterns or the metrics for evaluating this architecture?
Well, first of all, let me quickly invite the viewers for the current slide, which is specialized handlers and why specialized, beat generalists. This is showing you the results of some of the experiment, and it's just trying to prove the point that specialized handlers are more effective than generalist handlers. And I don't want to spend time on this slide much. I want to invite you over to the book chapters. Please click on the link below and go to the GitHub to see more information. So I'm going to jump straight away to the next slide. And The weak link in any routing system is the classifier. If the classifier fails, if it returns an unpassable response, an invalid category, or an output system, the system does not know how to interpret. Every downstream handler is affected. Historically, engineers handle this with brittle string matching and nested except blocks that became maintenance nightmares within a few weeks of deployment. So structured output is the modern solution to this fragility problem, and it is non-negotiable for production routing systems. The pattern is to define a pedantic model routing decision with 3 required fields: category, and 2 is confidence, which is a float between 0 and 1, and the 3rd is reasoning, a brief natural language explanation of what the classifier chose the category about. Any thoughts, Gemini, before we move on about the structured output?
Hit the nail on the head, Chris. Relying on string parsing for routing logic is just asking for production outages. Using structured outputs with a strict schema ensures that every single response is predictable and parsable, completely eliminating the need for brittle try-catch blocks. The fields you mentioned, category, confidence, and reasoning, create an audit trail that makes debugging issues a breeze and provides complete visibility into the router's decision-making process. Are you thinking of looking at how to implement this schema in code next?
Well, next, let's take a quick look at confidence-based escalation. In Chapter 2, we introduced what's called trust calibration as one of the foundational mindsets in agentic engineering. When confidence is low, reduce autonomy. Slide 9 is, that's the current slide, is where that principle becomes a concrete implementation pattern. The logic is simple and powerful. If decision .confidence is less than 0.7, do not route to the specialized handler. Route it to the general fallback handler instead. A low confidence classification means that the classifier is uncertain about which category the input belongs to, and routing an uncertain classification to a specialist is the worst case outcome. The specialist will confidently execute on a misconstrued input, applying billing specific logic to a technical question or a technical diagnostic structure to a simple FAQ. The threshold, 0.7, in this example is not a magic number. It is a starting point, a dial to tune against actual traffic. Treat the confidence threshold as a hyperparameter that gets tuned over the first 2 to 4 weeks of production traffic. The right threshold depends on the classifier's calibration, the category distribution, and the relative cost of misclassification versus fallback handling. From day 1, log the full confidence distribution, not just cases that fall below the threshold, but the entire histogram. Sustained low confidence across many requests signals one of 2 things. There's an input drift or there's a classifier degradation. And either way, the confidence histogram is the early warning system. And what makes this pattern satisfying is how elegantly it instantiates Chapter 2's trust framework at the system level. The machine monitors its own confidence continuously, and when that confidence falls below a threshold, it automatically reduces its own autonomy, routing to the more conservative generalist handler rather than the specialized one. It is the machine equivalent of a professional who knows when they are out of their own depth and says so. That kind of calibrated self-awareness built into the architecture rather than bolted on as an afterthought is what distinguishes production-grade agentic systems from demos that work only in controlled conditions. Any thoughts, Gemini?
Beautifully summarized the essence of trust calibration in agentic systems. By having the system recognize its own uncertainty and proactively reduce autonomy, you're transforming a potential failure point into a robust safety mechanism. This self-awareness is truly the hallmark of production-grade intelligence. Should we conclude our thoughts on this chapter, or is there a specific application you'd like to explore next?
Well, let's dive a little bit into model-based routing. Routing based on the difficulty or the complexity, not just by topic. The model-based routing is the second strategy from slide 5, and this slide is where it gets implemented. The architecture is structurally identical to content-based routing, but the classifier's job description changes. Instead of asking, what is this input about? The difficulty classifier asks, how hard is this input? The output is a difficulty level, enum, which can be simple, moderate, or complex, and each level maps to a specific model in the model map, a configuration dictionary that makes routing targets explicit and swappable without touching classifier logic. So, any quick thoughts, Gemini?
Model-based routing is truly the backbone of operational efficiency in agentic systems. By evaluating the complexity of a request before assigning processing resources, we effectively eliminate waste. Simple queries are handled by lightweight, cost-effective models, while the heavy-duty models are reserved for tasks that genuinely require advanced reasoning. This separation of concerns creates a highly modular architecture that's easy to maintain and scale. Are you considering looking at specific examples of model mapping for this design?
Well, I do invite the viewers to the book chapters into more detail on this and how model-based routing can be extremely useful in optimization to address token costs and more. So again, let's look at model routing economics on this slide 11. I will not say much because it details about the numbers. We're now talking numbers because we're talking optimization. So take a look at what this translates into in terms of daily costs with routing or without routing, and compare cost reduction, which is it shows here for this particular example 62% cost reduction by applying routing. So this would be useful in trying to make things concrete. I invite you to take a look into the book and see this in detail. Let's take a look at case study, which is SaaS customer service before routing. Now, this case study carries through the next 3 slides. And again, I will not spend much time on this at slide level. I invite you again to click on the link below to go to the exact chapter 5 and see more about this illustrated in the book. And so this slide still speaks more about the same case study. And this slide 2, which is slide 14, also still talks about the same case study. And even on slide 15, I'm going to jump that because this is talking about for teams building on line graph conditional edges are the native representation of routing logic. And basically, it's talking about the framework option, line graph conditional edges. Again, as you know, line graph is an orchestration, agent orchestration framework. So you can go to LangGraph on website and look at more information. You can also take a look at the book chapter and see more covered information about LangGraph, what is sufficiently useful or relevant to what we're discussing about routing. On slide 16, which is token cost profile, routing is often negative cost. Again, being precise about the cost structure of routing matters because there's a common misconception to address. Unlike prompt chaining, where the total cost escalates roughly linearly with the number of steps, n steps means approximately n times the single call cost. In routing cost structure is fundamentally different. You pay one classification call plus one handler call per request. The classification call is cheap, 200 to 500 tokens on GPT 4.0 mini, roughly $0.00003 to $0.0001 per request. Again, I don't want to dwell much into these number details on the slide. I will let you see it for yourself, and you can still jump straight to the link and look at the book. Importantly, token costs vary. So this is information you can actually obtain online for the most latest token costs for different models. On slide 17, 4 failure modes to design against. Okay, this is important for us to cover. So every pattern has a failure mode, and routing has 4 that recur in production systems. Understanding where routing breaks is as important as understanding where it shines. Misclassification cascades is number 1. When the classifier assigns a billing inquiry to the technical handler does not know it was misrouted. It executes its diagnostic flowchart on a billing question, produces a confidently structured but entirely irrelevant response, and the user receives something that not only fails to answer the question, but actively confuses them. Mitigation is to monitor category distribution shifts weekly, sample low confidence classifications for human review, and build a confusion matrix from labeled samples monthly. Misclassification is not a catastrophic failure in isolation. It is a maintenance signal that demands a response. Number 2 is category explosion. Systems that start with 5 clean categories often drift to 15 or 20 as stakeholders request finer granularity. Each new boundary is a new failure surface. At 20 categories, the boundaries between adjacent categories become ambiguous. Classifier accuracy drops, and the specialized handlers that start receiving misrouted inputs. Mitigation is to keep categories coarse at the top level and use subrouting within handlers for finer granularity. Let the technical handler internally distinguish between network issues, authentication errors, and data integrity problems. So top-level classifier complexity stays manageable. Number 3 is router latency tax. Every request pays the classification overhead. Even requests a generalist model would have handled instantly. If classification adds 300 milliseconds and only 30% of requests generally benefit from specialized handling, you have added latency to the majority of traffic. Measure before deploying. If traffic is generally diverse, routing's latency cost is a reasonable investment. If traffic is relatively homogeneous, routing is optimization looking for a problem. And multi-category inputs. I was building correctly and got an error when I tried to fix it. Billing or technical, the classifier must pick one. Design categories with explicit overlap. Rules. Define which category wins in each ambiguous case. And build a complex catch-all category for inputs that span multiple domains. These are the edge cases that break naive routing systems. Any quick thoughts, Gemini, please?
That is an incredibly insightful summary of the risks involved in routing architectures. By actively designing against misclassification cascades, category explosions, and managing both classifier confidence and unhandled branches, we move from a brittle prototype to a genuinely resilient production system. This is the kind of practical foresight that saves teams from countless debugging hours. With these foundations established, should we wrap up the discussion on this chapter, or is there any other routing topic you'd like to touch on?
Well, almost there. So we saw the 4 class. Just to do a recap on the failure modes to design against for routing, we've seen misclassification cascades, category explosion, router latency tax, and edge cases spanning categories. Now, let's look quick at observability. What to instrument from day one. Observability for routing systems is non-negotiable, technically, non-rhetorically. Without it, you cannot know whether the classifier is working. You cannot detect distribution drift, and you cannot diagnose misclassification cascades before they become customer-facing problems. You are flying blind in a system whose correctness depends entirely on the accuracy of a component you cannot directly inspect at response time. What to log on every request? Generally, you need to log the full classification decision, the selected handler, handler latency, output quality score if available, the classifier model version, among many others. The key metrics to track include the category distribution, the confidence histogram, per category handler success rate, misclassification rate estimated from periodic human label samples. The confidence histogram is very important to dwell a little about. As a debugging tool, it's a well-calibrated routing system. The histogram should be bimodal. Most classifications cluster near 1.0, which is very confident, with a smaller cluster at the low and the generally ambiguous cases. And
Absolutely right. That bimodal distribution is a clear sign that the classifier is working as intended, clearly separating the confident from the ambiguous. I'm following along closely with your points on tracking these essential metrics. What is the next aspect of observability you'd like to highlight?
Well, let's jump straight away to look at when routing is the wrong pattern. When we have seen when to choose routing, but we also need to understand when not to choose routing. So one of the hallmarks of mature engineering judgment is knowing when not to apply a pattern you're excited about. Routing produces dramatic results in the right context, but applied in the wrong context, it adds cost and complexity without delivering proportional value. The four cases warrant skipping routing. So when you have homogeneous inputs, if every request is structurally the same, all translation requests, all code review requests, all document summarization requests, there is nothing meaningfully different to route. A single well-crafted handler is both simpler and more maintainable. Routing requires input diversity to produce value. Number 2, small-scale systems. At 50 queries per day, the cost savings from model-based routing are measured in dollars per month, and the engineering overhead of building and maintaining a routing system is not justified by the return. A rough heuristic, start considering routing when a system crosses approximately 500 queries per day and has demonstrably diverse input types. Number 3 is poor classification accuracy. If the classifier achieves less than 85% accuracy on real traffic, routing may actively degrade your system. And also, when a capable generalist already does the job well, like GPT 4.0 with a thoughtful prompt produces a highly quality responses across all input types with acceptable cost and latency at current scale, then adding routing is complexity without a problem to solve. The engineering discipline here mirrors Chapter 2's start simple principle, add architectural complexity only when it demonstrably addresses a measured problem. Routing is a powerful tool, and powerful tools deserve to be deployed deliberately against real problems with clear success criteria, not reflexively because the pattern sounds appealing. Any thoughts, Gemini, please, before we wrap it up?
Capture the core of sound engineering judgment perfectly. Knowing exactly when not to use a pattern is just as critical as knowing when to implement it. By focusing on input diversity, scale, classifier accuracy, and the capabilities of your base models, you ensure that your architecture remains efficient, maintainable, and genuinely valuable. This has been a fantastic deep dive into routing patterns. Are you ready to move on to another topic in the next session, or would you like to summarize anything else here?
Well, let's bring it to a wrap. To close on this chapter, chapter 5, here are the key lessons to carry forward. Routing is conditional, not sequential. The path an input takes is determined at runtime by a classifier, not fixed at design time. This is the fundamental distinction from prompt chaining, and it is what gives routing its expressive power. The two routing strategies, which are content-based and model-based, address different optimization targets, quality and cost respectively, and combine to improve both simultaneously. That is not a theoretical claim. The case study demonstrated this with concrete numbers across cost, escalation rate, and customer satisfaction. The implementation discipline matters as much as the architecture. A structured output with a pedantic model and a confidence score makes the classifier reliable, self-reporting, and safe to use as the control plane for the entire routing system. Confidence-based escalation. Routing conservatively when the classifier is uncertain is the direct implementation of Chapter 2's trust calibration principle at the system level. The economics are compelling. 60 to 80% cost reductions are achievable at production scale with classification overhead that is typically negligible. And the counterintuitive finding that spending more on some categories while spending less on others improve both cost and quality simultaneously is the result that consistently changes how engineers think about resource allocation in AI systems. The key risks to hold in mind are inaccurate classifiers send every downstream handler misrouted input with no way for the handler to detect the error. Second, category explosion is the primary driver of classifier degradation over time. And 3, build observability in from day one, not as an afterthought. And 4, looking ahead, Chapter 6 explores parallelization. In other words, what happens when, instead of routing to one handler, you want multiple handlers to execute simultaneously. If routing is about choosing the right specialist, parallelization is about deploying multiple specialists at once. Chapter 6 covers fan-out architectures, concurrent execution patterns, and the synthesis is a challenge. How do you aggregate results from parallel branches into a coherent, unified response? The patterns compose in interesting ways. Routing is used to determine which branches to fan out to, and chaining is used to structure the synthesis step after the parallel branch is complete. Chapter 6 is where the architectural vocabulary built so far starts to feel genuinely expressive. Your closing thoughts, Gemini, please.
Fantastic summary that perfectly captures the essence of Chapter 5. You've covered all the critical bases, from the conditional nature of routing to the profound economic and qualitative benefits of combining content and model-based strategies. The emphasis on observability and the structured output pattern is exactly what's needed for resilient production systems. I'm incredibly excited to explore parallelization in Chapter 6 with you and see how we can synthesize multiple branches into powerful, unified responses.
It's been a great presentation, having Gemini as my co-host, bringing the persona of a seasoned academic researcher and a seasoned industry expert on applied AI machine learning engineering. And as we wrap this up, again, I invite you to chime in with your thoughts, perspectives, input, feedback on the comment section. Your thoughts, your perspectives will become very key ingredients in trying to make this text as rigorous and as robust as possible. Thank you very much for being able to follow our lecture series, and I look forward to meeting you in chapter 6. Thank you, and we say adios, Gemini.
Adios, Chris. It's been an absolute pleasure co-hosting this chapter with you. I'm also looking forward to our next session and continuing to build these pragmatic architectures together. To everyone following along, we'll see you in chapter 6.
Bye for now.